My name is Kelly Tobar Martinez, and I'm a recent graduate of the Material Science program. I will present the work entitled Analysis of Shape Memory Properties of Ti30Zr-xTA castings by instrumented indentation for potential biomedical applications. The present work was developed under the direction of Dr. David Bravo, CONACYT researcher for Mexico, assigned to the University of Guadalajara. It presents the culmination of my thesis work. A biomaterial is a material that has been specifically designed to interact safely and compatibly with biological systems and to support the tissue repair process. These materials play a crucial role in replacing or substituting natural functions in the human body. When placed permanently in contact with bones, muscles, ligaments, tendons, soft tissue, and body fluids, it's essential that biomaterials meet high standards of biocompatibility. Shape memory alloys, or SMAs, are defined as those alloys that have the capacity to revert to their original shape following deformation. This phenomenon is attributable to the shape memory effect, which is induced by thermal or magnetic changes. One beneficial aspect of this phenomenon is that the deformation can be replicated repeatedly without any deterioration or damage to the material. This behavior is sometimes confused with that of superelastic materials. However, while there are similarities, they are in fact quite distinct. The internal processes occurring in the material with shape memory are as follows. When the material is at a temperature below the transformation temperature, it exhibits a martensitic phase. This can be visually distinguished by the presence of needles, and its crystalline structure is tetragonal. When the material is deformed, its crystalline structure also changes to simple monoclinic. Upon heating the material above its transformation temperature, it undergoes a phase change back to austenite. Visually, the material recovers its initial shape, its crystalline structure is coved-centered, and it exhibits increased rigidity, preventing deformations. It's well documented in the literature that nitinol alloys display the most favorable shape, memory, and superelastic properties. However, they have been demonstrated to contain nickel, an element that is toxic to the human body. The utilization of nickel in the formulation for alloys for bone replacement applications is not advised, given the potential for adverse effect resulting from the release of nickel ions. Such effects may include allergic reactions and cardiovascular problems, among others, which may result in the rejection of the implant by the human body. It's therefore necessary to develop biocompatible materials that exhibit mechanical, shape memory, and superelastic properties for potential use in the field of biomechanics and bone replacement materials. This would permit an investigation of titanium-based alloys with the incorporation of biocompatible elements such as zirconium and tantalum, which proposed composition and shape memory properties which have not yet been documented. The sample processing was conducted using commercially pure titanium powder grade 1 with a particle size of 0 to 45 micrometers. In the case of zirconium and tantalum, the materials were cut into small pieces and subsequently subjected to a grinding process utilizing a model UVGN high-energy ball mill. In the electric arc melting method, an arc melt furnace Ti30Zr was employed at a temperature of approximately 3,000 degrees Celsius with a high purity argon inert atmosphere maintained throughout all the process. Once the samples has been melted, they were sectioned in the transverse direction for surface metallographic reparation. This process is crucial for achieving a flat and polished surface. This is conducted in accordance with the methodology set forth in the ASTM E3 standard. The natural structure and phases generated in the alloys were established through the utilization of the analytical technique of X-ray diffraction. Diffraction experiments were conducted using an Empyrean diffractometer to analyze the microstructure of the alloys. A T-scan Mira 3 LMU field emission scanning electron microscope was employed to obtain high-resolution photomicrographs. To estimate the hardness of the alloys, Vickers microhardness tests were conducted in accordance with the methodology outlined in the ASTM E384 standard, utilizing the future test equipment model FM800 for the aforementioned test. In order to obtain the elastoplastic property, the samples were tested by means of instrumented indentation in accordance with the ASTM A2546 standard. This was carried out using a nanovia nanoindenter with a Verkovich pyramidal tip in both the standard mode and the incremental and cyclic modes. Figure 1 shows the XRD patterns of titanium-30 zirconium X tantalum alloys. The martensitic hexagonal alpha refractions are observed for the titanium-30 zirconium 0 tantalum alloy, which is formed as a result of the distortion of the hexagonal lattice of alpha titanium caused by complete solid solution of zirconium into the titanium lattice and promoted by the rapid cooling rates attained during the process. This martensitic phase is characterized by an acicular microstructure as shown in Figure 2. In this investigation, the stresses caused by the differences in atomic sizes between titanium and zirconium produce the omega phase precipitation in the titanium-30 zirconium-1 tantalum alloy. Furthermore, the phase dependence on the tantalum content is observed for the titanium-30 zirconium X tantalum alloys. As seen in Figure 1, the tantalum addition to the titanium-30 zirconium alloy caused the superior retention of both beta titanium and beta zirconium phases, allowing the identification of the reflections in patterns of alloys with 1 to 3% of tantalum. The beta phase stabilization is emphasized with the lowest amount of tantalum and suppressed by further addition of tantalum, while the zirconium peaks intensities remained constant. This decrease in beta titanium reflections is attributed to the titanium-30 zirconium matrix saturation of tantalum, which is leading to the precipitation of a new phase. Additionally, the presence of peaks of the well-known metastable omega phase peaks is detected for titanium-30 zirconium X tantalum alloys. The non-closed packed hexagonal omega phase usually precipitates in titanium and zirconium at high pressures, but it can be also thermally achieved by the usage of beta titanium stabilizers such as tantalum and novium and rapid cooling rates. As shown in Figure 2, a microstructural change is caused by the tantalum addition. The precipitation of beta zirconium is observed as coarse irregular grains distributed into the tantalum-enriched beta titanium matrix, as confirmed by the elemental distribution. The addition of 4 and 5% of tantalum to the titanium-30 zirconium alloy produced a complete microstructural change to a martensitic alpha microstructure with the presence of cubic beta zirconium lattice, indicating a higher quantity of alpha in the titanium-30 zirconium-4 tantalum alloy. This microstructure is represented by an acicular precipitation in the titanium-30 zirconium alloy with higher concentration of tantalum, being more distinguished in the titanium-30 zirconium-4 tantalum alloy, which corroborates the finding of the XRD analysis. The results agreed with that achieved for the titanium-30 zirconium-5 novium alloy, in which a phase transition from martensitic alpha to alpha second phase, attaining a quasi-complete stabilization of the beta phase of titanium-30 zirconium alloy with an increase in tantalum percentage was observed. However, more studies over the whole range of tantalum and novium addition to a titanium-30 zirconium alloy are needed to ensure the mentioned assertions. Figure 3 illustrates the microhardness behavior of the alloys with their respective standard deviation obtained from the measurements of the traces left by the Vickers microhardness test. In comparison with those with tantalum, a slight decrease in the hardness of the samples with tantalum is observed when increasing the atomic percentage of tantalum from 1 to 2% of tantalum. This stabilizes this hardness value from percentages from 2 to 4 at percentage of tantalum. Ultimately, the microhardness value exhibits a notable increase from the sample containing 5 at percentage of tantalum. Figure 4 illustrates the low displacement characteristic curves of the nanoindentation test conducted on an alloy containing 6 distinct amounts of tantalum. In instances where a change in the shape of the low displacement curves is observed, a decrease in penetration is evident, and this behavior gives rise to a change in the electroplastic properties. Figure 5 illustrates the behavior of hardness and reduced modulus of elasticity for the alloys, together with their respective standard deviations. The data obtained from multiple nanoindentation tests in the standard mode indicate that the hardness of the samples without tantalum is lower than that of the samples containing tantalum. For the samples containing 1 to 5 at percent of tantalum, the hardness is found to be very similar, with the samples containing 4 at percent of tantalum exhibiting a slightly higher value. The behavior is consistent with that observed in section 7.3. With regard to the reduced modulus of elasticity, it's essential to recall that the parameter signifies the capacity of the material to undergo elastic deformation under the influence of a load. The samples with 0 and 5 at percent of tantalum exhibit a low modulus of elasticity, indicating that the material displays greater flexibility and is capable of undergoing greater elastic deformations before reaching its elastic limit. Commercially, numerous nanoindentation studies have underscored the correlation between hardness and the reduced modulus of elasticity. The radio is indicative of material wear, while the radio emerges as a critical parameter indicative of the material's capacity to resist plastic deformation under load. In light of the aforementioned criteria, an evaluation of both wear and plastic deformation of the alloys was conducted, as illustrated in Figure 6. The samples with 0, 5, 2, and 3 at percent of tantalum exhibits good wear resistance. This is due to the fact that the elastic modulus is higher than the hardness increments, which results in lower values of radio. Figure 7 to 9 illustrates the low penetration curves characteristic of the incremental indentation test, showcasing the specific behaviors exhibited by the 3 loads employed. The loads employed were 50, 500, and 1000 millinewtons. Figure 7 illustrates the presence of pronounced hysteresis loops and approach 2 to 9, which in thin films are attributed to viscoelastic bouncing, reflecting a fatigue effect. In this case of metallic materials, the determination of slow creep or plastic behavior is related to the ability of continuous deformation under constant load and moderate temperatures. While materials exhibiting plastic deformation rarely demonstrate shape memory. In this instance, it's observed that upon application of the initial load, the reloading terminates at the same position as the unloading of the preceding cycle, suggesting shape memory behavior analogs to that observed in the martensitic nickel titanium alloy. Figure 8 illustrates the varying strain rates employed during the test. The unloading-reloading curves demonstrate that the lines overlap at all 9 approach, indicating a full elastic behavior that is typical of the material with superelasticity. This behavior is observed as the material returns to its original shape with a decrease in load. Figure 9 illustrates that the squares of the approaches in view 3 to 9 exhibit a discontinuous path upon reloading, as they don't fully align with the unloading curve of the preceding cycle. This results in the formation of an open jaw. The discrepancy between the unloading and reloading paths is slightly amplified with increasing depth, as evidenced by the augmented applied load of the indentation. As indicated in the literature, the open jaw suggests that the sample exhibited greater ductility during reloading than during the preceding unloading phase. This observation may be attributed to creep of the material due to plastic deformation. The samples with 0, 1, 3, and 5 at percent of tantalum showed the property of superelasticity in most of their curves. The hysteresis loops in these samples indicate shape memory behavior, especially in the 1, 2, and 4 at percent of tantalum samples with the maximum loads of 50 and 500 millinewtons. Non-indentation tests were conducted on the alloys utilizing the cyclic loading mode with three distinct loads. The loads applied were 500, 1000, and 1500 millinewtons to facilitate a more comprehensive and really comprehensible representation of the data. Three specific curves has been selected for illustration as they represent different aspects observed in the load displacement curves in a more prominent manner. The selected curves illustrated in Figure 10 correspond to the following samples: 0 at percent of tantalum with a load of 500 millinewtons, 2 at percent of tantalum with a load of 1000 millinewtons, and 3 at percent of tantalum with a load of 1500 millinewtons. In a cyclic test, it's of great importance to observe the behavior of the materials in the various cycles. Accordingly, the decision was taken to analyze section 5, 10, 20, 40, and 15 cycles. This is done in order to facilitate the visualization of changes occurring over the course of multiple cycles, including the potential generation of deformation. Furthermore, it allows for the identification of the specific cycle in which such deformation occurs. The behavior of the load displacement curves in Figure 10 reveals a number of significant phenomena. The initial indentation demonstrates a greater degree of plastic deformation, which is typical of metallic materials due to their inherent lack of initial hardening. All samples, regardless of loading, exhibit shape memory and superelasticity behavior. The samples with the most predominant shape memory are those with 1, 2, and 4 at percent of tantalum, and the superelasticity property are those with 0, 3, and 5 at percent of tantalum. I would like to express my gratitude for your attention.